Okay. Hi, everybody. I hope you can hear me all right. I'm just going to get started. I'm going to do what happens in class where students at this time of the semester aren't showing up on time. I'll just start. So I get to introduce myself, and so I can keep it short. Wes Waters is my name, and I am a professor in the Department of Physics and Astronomy at Wellesley College. And I'll say a little bit about what I do in a minute. But first, I want to acknowledge a few colleagues with whom I've had a number of very nourishing conversations, and some of them are here. Mike Safone is here, and Kevin Knuth, and Hussein Aliagrama. I'll be talking about an analogous situation in history, and that is the story of meteorite falls and how they were denied for a long time. And I think there are some striking parallels, because it's an unusual kind of anomaly, and UFOs are a similarly unusual kind of anomaly, and science digests these anomalies in a similar way. But first, let's see if I can get this going. Okay, so my main connection to the UAP topic is that I've been heavily involved in the Galileo project since the beginning. And on the Galileo project, we're building what we call a multimodal observatory, what we call an observatory class system or instrumentation platform that measures very many different physical parameters to characterize the environment, but mainly to track objects in the sky, detect them, and characterize them. So we've been hard at work developing models and methods to do that and instruments to do that. And as a kind of side quest at Wellesley College with my students, we've been building relatively inexpensive instrumentation platforms that one could in principle distribute through a region, and that are, like I said, relatively cheap. They're commercial grade instruments that we calibrate, so we turn them into scientific instruments. They don't start out that way. And so 3 of them that you can see on the screen here are our flagship instruments. And so I have, in the process of working on all this and thinking about UAPs, become even more interested than I was before in anomalies and how they operate in the history of science. So that's what I'm going to be talking about today. So my training is in physics and planetary science, and for most of my career, I've focused on impacts and what happens when rocks collide with planetary surfaces at really high speeds. And so what you see on the screen right now represents the desolation of small airless worlds. This is the surface of the moon, which they tend to be covered with impact craters. So I studied the process that generates this kind of landscape. And what happens when rocks hit the surface of planets when they're traveling tens of thousands of miles per hour. So this is the process that, in addition to producing landscapes like this, and by the way, we've only been confident for about 60 to 70 years that lunar craters were generated by this process. Also, there's a moment in my own personal story that intersects with the history of meteorites. And that happened when I was on the Mars Exploration Rover science team in the early 2000s. And while we were crossing the surface of Mars, we decided to visit a terrestrial spacecraft that was, or a piece of one that was deliberately crashed on the surface of Mars. This is the heat shield that protected the rover during its transit through the atmosphere. And by coincidence, just a few tens of meters away, there was another object that we certainly didn't put there that was glinting in the sun, and it was this. We immediately recognized it as an iron meteorite. And it was the first, to my knowledge at least, the first meteorite ever discovered on the surface of another planet. So that was pretty exciting. And I mention all of this because what I'm here to discuss, the story of a phenomenon and the study of a phenomenon, a meteorite falls, which was for centuries denied by savants, let's call them, to happen on our planet. And it turns out it's actually a ubiquitous process. So it happens all over the place. It's prevalent throughout the universe. And not only that, but it's also foundational, because this is the process that built the planets. This is the process that built our planet. our planet formed by chunks of rock and ice colliding at high speeds. So that's quite a trick, right? To go from a phenomenon that was denied for a long time, or at least not considered to be very important, to, it turns out, being the process that makes the world. And that's an extraordinary transition. So I'm going to talk to you about the origins of my field. So as a planetary scientist, the story that I'm telling you, I don't study meteorites, but the story of planetary science in a way begins with what I'm going to explain. And it has relevance to the UFO question partly because it's very often evoked as having a special relevance to that problem, but not necessarily with a lot of comment or deep reflection. There are a lot of similarities and there are some important differences, and I don't even think I need to call them out explicitly. I think they'll be fairly clear to you. So I'm interested in this because I think it might give us some insights about how a transition in thinking about something like UFOs could take place. And so I'm going to focus on the barriers to acceptance of the reality of the phenomenon, as well as what kinds of events and what kinds of interventions were necessary for this transition to happen in the case of meteorites. And I think that will be illuminating of our present historical circumstance. And I should say, I'm not an intellectual historian. Okay, I'm a scientist. I'm not a philosopher of science. So I'm leaning on the work of historians to talk about this. And so I am, to some extent, traveling outside of my lane. Sorry, but not sorry, because it is the history of my field, and scientists should be acquainted with the histories of their fields. It makes us better scientists. I feel that's very important, and so I talk about the history of science a lot in my classes. All right. So falling stones were an anomaly in the context of 17th and 18th century science, and for our purposes, we'll define an anomaly as an observation or a phenomenon that is unexpected and that resists explanation in terms of prevailing beliefs about the world, scientific beliefs and practices in this case. So we'll need to identify those beliefs, and I'll do that in a bit. So scientists always essentially always are conducting their work inside of a framework of theoretical ideas and methods, and that's been called by a lot of different names. Sometimes it's called a research program. Imre Lakatos called it a research program, or a paradigm. So Thomas Kuhn famously called it a paradigm. And Kuhn compared what most scientists do to a mopping up operation. So in other words, there's a theoretical framework that is established by an eminent scientist, and then other scientists are doing this mopping up operation. They're working on puzzles, and puzzles, of course, are guaranteed solutions, right? So as long as you're clever enough, you'll get to the solution of the puzzle, and then you get to advance as a scientist. So that's how he characterized what scientists do most of the time. And so what I think many people find surprising and counterintuitive is that anomalies are often ignored by scientists, at least for a while, because there's a tendency to trust that the prevailing framework will eventually get around to resolving them. So that there's some kind of an error, maybe it's a mistake, maybe it's an artifact, and that eventually it's going to go away, right? So from a practical perspective, I think we can understand this. If you want to advance as a scientist, you need to publish positive results, and there are plenty of well-posed problems out there, or puzzles out there. So why take a risk working on something controversial that may turn out to be a mistake of some kind, right? Maybe think about coming back around to it after tenure, if there's time. So many anomalies that are acknowledged and addressed in the physical sciences arise in the context of a deliberate scientific experiment and observations. In these cases, there's usually an expected outcome that derives from existing theory. And whenever there is an unexpected outcome, like a failed prediction, for a lot of scientists and a lot of the time when that happens, that's a headache. I mean, you've got a problem, potentially a pretty serious one. Sociologists Susan Starr and Elihu Gerson, they pointed out that anomaly is therefore sometimes at least an interruption of scientific work, because now you have a decision to make. Either you can ignore this and you can go back to working on puzzles or well-posed problems that are more likely to be successful, or you've got to do the hard work. You've got to do the hard work of figuring out whether this is a discovery, a mistake, or an artifact. And that can be really exciting. I mean, I know from personal experience that can be really exciting and really distressing at the same time, because you may end up making a controversial claim. And that's taking a risk, right? Okay, so what I'm showing here is an example of an anomaly, or actually a couple of anomalies that arose from deliberate observations by scientists who, or that was these two anomalies, I'll describe them in a moment, were completely confirmed, and it was a major discovery. And as you can see, this was published in 1815. This is Joseph von Fraunhofer's spectrum of the sun. So we have the brightness spectrum at the top, and then we have, you can see the color representation with these dark lines that are Fraunhofer lines that we now know to be associated with electronic transitions in the solar atmosphere. And the bright curve at the top, or the brightness curve, the spectrum, the brightness spectrum at the top, that's the black body spectrum. So these two anomalies posed a very serious problem at the end of the 19th century for classical physics and led to the emergence of quantum mechanics, which has totally changed the world. So these are the kinds of anomalies that can arise in the course of normal scientific work that turn out to be profound discoveries and then really have an impact. But meteorites, on the other hand, are not an interruption of scientific work. They're completely adjacent. There were rocks falling out of the sky, and people didn't really know what to do with that. This is residing outside of the ontological framework that natural philosophers were working in at the end of the 18th century and the beginning of the 19th century. So there wasn't even like a category for this inside of scientific parlance. And so for a lot of scholars at the time, this was just part of the social and cultural background noise. But even worse was that these weren't even reported by scientists or natural philosophers. I'll use those words interchangeably. It was coming from outside of that community, that trusted community. And a sociologist, Ron Westrom, in the 70s and 80s wrote about meteorites and the network of social intelligence that allowed these reports to percolate up to the savants and to the natural philosophers. So it was typically someone in the fields who would see this, and then it would get around to local officials and then make it to a savant eventually who might take an interest or might just laugh, as I'll discuss later. And he made the point that in the late 18th century, science was still a fledgling enterprise, and it was still trying to protect its boundaries. And so admitting data that came from outside the community that was not under the control of scientists, that was dangerous to the whole enterprise. And so they were very careful about kind of policing that to the extent they could. And so there was a lot of, anyway, like I said, skepticism towards these external sources of information. But there are other features that make this anomaly special, and that led to the situation that I just described. So meteorite falls are extremely rare, they're fleeting, and they can't be reproduced on demand. So that makes this really hard to study. And before I tell the story of that study and how all of this evolved, I want to say a little bit about how we understand the phenomenon today. So in general, a large rock hits the atmosphere, and it's traveling on average about 15 kilometers per second or 35,000 miles per hour, sometimes a lot more. And this creates an aura of incandescent gas around the object, and it's shining very brightly. The surface heats up and it melts and ablates, so material gets stripped away. And there's a zone of compressed air in front of the object that applies an enormous amount of pressure to the surface, and then it breaks up, and then those smaller pieces are more effectively slowed down by the atmosphere. So they hit the ground typically at like between 100 and 200 meters per second, and that would be the meteorite. Okay. But on the other hand, and there's also oftentimes a thin crust, a thin black crust around the edges, which you can see here in this example. And that's what's called a fusion crust, so that's the melted layer, and it's only about 1 millimeter thick, so the heat doesn't penetrate very far. And so if the object, on the other hand, is large enough, then it can make it all the way to the surface of the planet, moving at supersonic speeds, then it forms a crater, and then it gets completely destroyed. So that's a thing that happens too. Okay, so this is these frames that I'm showing here relate to the Chelyabinsk event, which happened. It was an airburst event, the most powerful ever witnessed and recorded in modern times. It happened by large numbers of people, I should say. So this was a large number of people who saw this. So this was on the 15th of February of 2013. And this is in the Urals in Russia. You can see the dust cloud in the upper left there, and then there's a fireball in the lower left. And windows were shattered for tens of kilometers around by the shock wave. And so that is not something that we see every day for sure. This is a very unusual event. About 4 to 6 tons of rock made it to the surface. That's a tiny fraction of the original amount. And it was maybe 20 meters across when it hit the upper atmosphere, and it released about 30 Hiroshima bombs worth of energy in the upper atmosphere. And there were hundreds of injuries, thousands of witnesses. So to be clear, usually no material hits the surface of the planet, but more often than not, it's just a few rocks hit the surface, and only, if anybody, I mean, usually nobody sees that, right? But if anybody sees it, it's a handful of people. Even though the fireball, lots of people will see the fireball, but only a few people will see the rocks fall. So that's part of the reason this was really hard for people to accept, because there were always so few witnesses. Not always, actually. It turns out there were quite a few in some cases. All right, so as often happens in science, there's a foundation myth about the origins of a discipline, and it's described in textbooks. And this is often used to illustrate some kind of moral lesson about how science works. Even though it's usually a dramatic oversimplification, it's usually wrong in some important respect. And for some reason, it doesn't get fixed. It just keeps showing up in the textbooks. But one thing that's special about the origins of meteoritics, the study of meteorites, is that the foundation myth has been so useful to people who want to call attention to blind spots in the history of science, or blind spots in science that, when noticed, can lead to major upheavals in the way we think about the world. And it's also been useful to people who want to call attention to the importance of eyewitness testimony. And interestingly, people on both sides of that question use this myth in an interesting way, or this story in an interesting way, and I'll talk about that. So here's an example of someone using it. This is from Jeff's most recent book, How to Think Impossibly, where he's talking about the need for new frameworks that actually make sense of anomalous experiences versus the collection of more data. So he wrote this. He said, "The analogy is not perfect," and that's true, but our situation is a bit like what educated people in the European cities of the 17th century thought of all those silly farmers in the countryside who kept talking about rocks falling from the sky. So I'm going to skip ahead a little bit. And he says, eventually they arrived at a new model of what outer space actually is. So while the arrival of the new correct framework, that was definitely important, it turns out not to have been the only or even the most important factor, since it was ignored for decades. But it was absolutely essential to making the transition. So what I'm showing here is a depiction of a fall at Einsiegsheim in modern-day France, where a rock fell in 1492. You can see the obliging farmer somewhere pointing up. Where is he? I've lost track of him. Okay, right here, yes, pointing up at the object. And so in this case, I think it was a child, it was a boy who saw this, and then villagers descend on the rock and start hacking it to bits because they want to use it as they think it has medicinal properties. I'll say a bit about that in a minute. But we know that this was a meteorite fall because the rock survived. It's now in a museum, and so we can confirm that it was a meteorite. So one of the challenges to engaging with this phenomenon in the late 18th century was, as Jeff implied, is that it was stigmatized. So there was a taboo surrounding the whole subject, and there was a folklore, which by the mid-18th century was widely ridiculed by scholars. So the few philosophers who were paying attention faced the challenge of having to distill the physical phenomenon from the folklore and from the popular interpretations of this, and this metaphysical baggage that had become attached to it, right? Let me give you an example, a really dramatic one. At 9:30 p.m. on the 24th of July of 1790 in southern France, there was a fireball that soared overhead, and it was witnessed by hundreds of people. There was a loud explosion, and then lots of rocks started raining out of the sky in Barbeton and Agen, these two villages in southern France. So the witness stories eventually reached a local savant whose name was Jean Saint-Amand, and he found the whole story completely ridiculous, and he thought he would have fun with it by daring them to basically sign an affidavit testifying to the event, their observation of the event. And he was completely shocked when they actually did this. And but this did not convince him that it had actually happened. This just convinced him that country folk are even more credulous than he thought. And so he told a friend of his who was an editor at the Journal des Sciences in Montpellier, His name was Pierre Berthelon, and this is what he wrote. So the readers, if the readers have already had occasion to deplore the error of some individuals, how much more will they be appalled today seeing a whole municipality attest to, consecrate by legal protocol in good form these same popular sensations which can only excite the pity not only of physicists but of all reasonable people. What can we add here to such an affidavit? All the reflections which it suggests will present themselves to the philosophical reader in reading this authentic attestation of an obviously wrong fact or a phenomenon that is physically impossible. Right, our favorite word. Okay, so Domenico Tata was a professor of physics and mathematics in Naples, and we have his memoir that attests to the chilling effect that this kind of ridicule had on scientists at the time who were interested in this problem. So he learned about a fall that happened in Calabria in 1755, and he wanted to write about it. He was curious about it. He also was very skeptical, but he thought it was worth writing about. But then his colleagues said, no, you don't want to do that because that will ruin your reputation. So he waited 40 years until the landscape started changing in the 1790s. That was a critical time. There was a shift there. And then he published his memoir and he writes about it. There had been a fall, a really spectacular one in Siena in 1794, so it was around that time that he was publishing his memoir. Okay, so they had to deal with ridicule and taboo. Sounds familiar, right? And then, in addition to that, there were lots of background beliefs to cut through, and anomalies stand out with respect to background beliefs, as I said before. So they are only noticed with respect to what people think is true about the world. And there are a few of these that are important. One of them, I want to make sure that I get the wording right. So this is something that Carl said. And there's a kind of a general attitude or maybe psychological imperative here, which is just the non-disclosure or maybe non-investigation of uncomfortable aspects of reality. And one could argue that the idea that rocks can fall from the sky at any minute and vaporize a city is an uncomfortable aspect of reality. So I have a feeling that had something to do with it as well. But in addition to that, there were a bunch of, in some cases, deeply entrenched beliefs, in some cases not. I'll just say what they are. So there was the idea that the sublunary realms, everything within the orbit of the moon, is a closed system. Nothing goes in or out of that. And that's that was a very old idea. So you can't have rocks coming in from interplanetary space and hitting the surface of the planet. And then what was believed about what happens in the atmosphere was mostly based on Aristotle's Meteorologica, you can see on the right-hand side. And this was not a mature science. So there were a lot of ad hoc explanations. There were some theoretical ideas that were implied imperfectly across a wide range of what were called meteors, which would include rainbows and parhelia and thunderstorms and so on. So it was kind of a morass of facts more than a science. And eventually what happens is that meteorology, this traditional meteorology, would become, on the one hand, atmospheric science, and then meteorology within that, which is about the study of the weather, and then the other thing that broke off of it was meteoritics, which is the study of meteorites, and that started to happen really at the end of the 18th century, beginning of the 19th century. Okay, so another one of these beliefs is that space is empty, apart from planets and stars and so on. Interplanetary space is just empty. Aristotle said so. Isaac Newton also said so, because if there's too much interplanetary debris, then okay, that's going to slow down the planets and they'll spiral into the sun. So that's reasonable. But trace amounts, there's no problem with having trace amounts of matter out there in interplanetary space. And so what's key there is that's a very flimsy dogma. That's a peripheral element of Newton's theory, and so it could be dispensed with. Even though people were attached to it for some reason, that was relatively easy to overcome, so that wasn't a big deal. It wasn't a deeply entrenched belief that a lot of other beliefs depended on. It didn't threaten Newtonian mechanics. Okay, but then there are other metaphysical attitudes and belief systems like deism, a flavor of which seem to assert that, okay, there was a prime mover that set everything in motion a long time ago according to inviolable physical laws, but did so in a way according to a plan that is providential, that is going to be essentially beneficial for human beings in the long run. And so there were some voices who were saying, well, the idea that rocks can fall willy-nilly from the sky and wreak havoc and cause this violence on the surface of the earth is certainly at odds with that, and that's inconsistent with the idea of a providential order to the universe. So there are some. So that's a more of a deeply entrenched belief that I think was loosening a bit by the late 18th century, and I'm talking about among natural philosophers. So not talking about the public at large, talking about the beliefs that are held by natural philosophers at the time. At least this is my understanding. And then there are an interesting set of beliefs about what are called figured stones or lightning stones or thunderstones, and these are magical objects. They're kind of like apports, actually. They sort of show up overnight, and sometimes with lightning strikes, and then all of a sudden they're there in the ground, and people collect them, and apothecaries would collect them and sell them as medicine and use them for other things too. So the problem it was that in the 18th century, scientists started to figure out that a lot of these things were prehistoric hand axes and fossils, but then there was this other subset that were these rocks that were encrusted with this black material, and what the heck are those? And so you had to do this hard work of distilling that from the rest, because if the rest have a prosaic explanation, and we know about the tendency for some people to say, well, probably all of them do if we just had enough information. And in this case, the other issue was that these were magical objects. And there was a movement underway in the 17th century and the 18th century to delegitimize marvels and miracles. There were a bunch of reasons for this. If you're interested in it, I recommend the book by Catherine Park and Lorraine Daston, who wrote beautifully about this. One of the issues was that they were so politically, at least potentially politically destabilizing, marvels and miracles were, at a time when Europe had survived these horrible wars of religion. And so there was that, in addition to other reasons that people wanted to undermine marvels and miracles, at least natural philosophers did. So it was really bad taste to be interested in the marvelous. Like, that was not part of the new scientific ethos, and scientists would accuse each other of that, of like making that mistake. Just like, I mean, today, that's still largely true today. Okay, so you have meteorites lumped in with the other things. Those are the background beliefs. Now, the new framework, or the question I want to address for the rest of the time is what led to the acceptance of the reality of the phenomenon, and then what led to the acceptance of the correct explanation. And first there was a new framework, and this was developed by a guy named Ernst Chladni, a physicist. He was the founding father of acoustics as well as meteoritics. And what's so interesting about this is that his paper, his treatise on this, was based on an archival investigation. He went to libraries and he collected lots of eyewitness accounts, about 20 of them, in particular about meteorite falls, almost 20. And he noticed similarities in the properties of the stones and in the descriptions of the falls themselves. And he came to the conclusion, this is his hypothesis, that we'll call it the interplanetary hypothesis. So, one, this phenomenon is really happening. So there are masses of iron and rock that fall from the sky. He's writing this at a time when natural philosophers do not accept that. Two, they produce fireballs due to frictional heating as they travel through the atmosphere. Okay, right on. He was wrong in some particulars, but for reasons that can be easily forgiven. And then three, these materials come from interplanetary space and derive from primitive materials that did not aggregate to form planets or that were blasted off planets in collisions and explosions. I mean, amazing, right? He used eyewitness testimony to come up with basically the right answer, and it would take another 60 to 70 years to finally agree that this is correct. So this did not convince the scientific community, but it was an important step on the way. Okay, and then there were lots of other attempts to kind of explain this away in the late 18th century. So one was that lightning maybe just happens to have an affinity for rocks that are pyritic, so that have sulfur in them. And then they strike these rocks, and they kind of char them, and then they get lobbed into or melt the outside, and they get lobbed into the air, and then they fall back down, and that's what the farmers are seeing. Even though the farmers were not seeing the lobbing into the air, they were only seeing the falling back down. Never mind, that's a potential explanation. And then volcanoes get blamed a lot, even though oftentimes there aren't volcanoes nearby or none erupting, but as you can imagine, Mount Etna, whenever it was erupting, could be blamed for this. And But there's a real process that forms in ash that gets ejected. They're called accretionary lapilli, these objects that form by accretion of ash and they fall to the ground. But so that could be a source of this, or just rocks get lobbed into the atmosphere by explosive volcanic eruptions, or maybe there's some kind of a condensate in the upper atmosphere, like hailstones, and they come down to Earth. So there were some interesting ideas, many of them trying to explain this away. And then there was what I'm calling a scaffolding hypothesis. So this is a hypothesis that raises the plausibility of something, that is, in this case, of rocks falling from interplanetary space, so that people can have a conversation about it. It softens the taboo. And this was the idea that rocks are being ejected by volcanoes on the moon. And it helps to have a very eminent physicist support the idea. So that was Pierre-Simon Laplace. He said, this might be right. And so a lot of people started to take this more seriously, and that's when the climate started changing in the 1790s. And people started to talk about this more and think about it more. So it really helps to have a bunch of mass sightings all in a row. This happened from 1794 in particular to 1798. There were like 4 of them. There was one in Siena in Italy, there was one in Portugal, in England, and also in India. And lots of people saw these, and then they were widely publicized and well documented, and that swayed a bunch of people, but it did not sway the scientific community. There was still most people were still on the fence in that community about even the reality of falls. So then, it was also very important that there was an invisible college of people who were interested in, like I was saying earlier, interested in this problem, and they were sharing materials, and then they were analyzing them in their labs using the new methods of analytic chemistry that were coming online at the time. So there was a new scientific technologies that could be applied to the problem, and that were giving people insights. And the most important insight that was published, for example, here by Edward C. Howard in 1802, using rocks like the ones shown on the right, the meteorites from Siena, is that they were finding this nickel-iron alloy. So this nickel in the iron so you have stony meteorites, and then you have iron ones, and there are flecks of iron in the stony ones, and inside those flecks of iron you had the same proportion of nickel as you do in the iron ones, and that was really interesting, because that doesn't happen in ash, that doesn't happen in any of these other processes that people had stipulated, and so it seemed to point to a cosmic origin. And that was interesting, but that didn't sway the scientific community either. In fact, this was met with a lot of scorn and derision, interest, but also scorn and derision, and even an accusation that the scientific integrity of the scientists had been somehow compromised in this process. And one critic even said, this is, let's see if I can find the quote here. So the love of the marvelous is the most dangerous adversary of science. So that was appended to one of the critiques of Edward Howard's work. Okay, and then 5, now this was the turning point. And this was okay, let me back up and say it's very important. There was a mass sighting, another event that happened in 1803. So this was in L'Aigle in France. This was 130 kilometers west of Paris. It happened in April of 1803. And the young Jean-Baptiste Biot, who went on to have a very eminent career as a physicist, he was sent out by the Interior Ministry of Napoleon's government to check this out. And so he went out and he wrote a beautifully written account of his journey that lots of people enjoyed reading. And it was reprinted in lots of places, so in lots of popular journals and so on. So Mathieu Gounel has noted that this was not a traditional scientific paper. It was a narrative, it was a travelogue in the expedition genre of people like von Humboldt and Charles Darwin. So it was the account of a journey to the countryside, of interviews with all the eyewitnesses, of assessment of the credibility of the witnesses from all social strata. Okay, and so, of course, by performing that calibration of witness testimony, you could also calibrate previous eyewitness testimony of country folk. Okay, So that was important. And he also noticed that the rocks have nothing to do with the local geology. And on the other hand, they're a lot like the rocks that scientists have been working on and publishing about. So he writes this account. It gets widely circulated, like I said. It's an account of one man going through this process of synthesizing all of this information and changing his mind and giving people an insight into that intellectual process. And that's what swayed the scientific community and those educated people in the cities that Jeff was talking about. And in 1803, that was the acceptance of the reality of the phenomenon. And this is a map on the right-hand side of where the meteorites were found. Okay, I've got to hurry up, but I'm almost done. So there were adjacent. So that's the acceptance of the reality of the phenomenon. Then for the rest of the next, then it took a while for the correct explanation, Chladni's explanation, to be accepted. So I'll just mention that a couple of examples. The asteroids were discovered, so then you had a source for these materials. This really picked up in the middle of the 1800s. And then here's an example of a discovery that could have been made any time in the 2,000 years preceding it. And that is that there is a point in the sky from which all meteors radiate during a meteor shower. And that is called the radiant, and that point tracks the celestial, it tracks the celestial sphere. So that's why we name meteor showers after constellations like the Geminids or the Perseids. So it tracks the celestial sphere, not a position in the atmosphere. So this is a cosmic phenomenon. And that was a major discovery that helped people to understand and connect a few dots as well. So it wasn't until 1860 that Chladni's hypothesis was finally accepted. I don't have time to talk about this, but I'll just mention that there was a transition from a retrospective and forensic investigation to a prospective investigation, where people go from like studying and piecing together what happened to trying to make observations of new events, or in the case of this Weston, Connecticut meteorite fall, when there was a big fireball, Benjamin Silliman set out to try to find it, right? So there are deliberate attempts to retrieve materials. And he wasn't, but others were successful in getting these rocks, and he was able to study them. But also there were efforts to triangulate meteors in the atmosphere. This is what we're trying to do with UAP. And they discovered that these events are happening in the upper atmosphere. They're not happening in the lower atmosphere. So again, a sign this is a cosmic phenomenon. Okay, now I just want to take time to get through this. This is really important. There were some, because I did mention at the beginning that this story is used by people on both sides of the debate about the importance of eyewitness testimony. And, whoops. And so Ursula Marvin, who is a historian who wrote some of the histories that I've been relying on for this, she remarked in her paper in a paper in 2006, that there's a problem with eyewitness testimony in these situations because so many of the witnesses claim that meteorites are hot to the touch. But every meteoriticist knows that can't be true, because the meteorite's been in outer space, so the interior is really cold. As it passes through the upper atmosphere, sure, it heats up on the outside, but that only goes a millimeter deep. And then it cools off while it's reaching terminal velocity, and then once it's on the ground, it's cold again, or cools off very quickly. So meteorites can't be hot to the touch. They must be imagining that. And then there's also the idea that lots of people would report brimstone, or the smell of sulfur and this kind of burnt smell. And somebody else noticed, it wasn't Ursula Marvin, that the brimstone part, the sulfur part, went away at a certain point when brimstone was no longer associated with these events in the popular imagination. So in other words, it was chalked up to the power of suggestion, both the sulfur smell and the hot to the touch, right? Well, you know what I'm going to say next, right? So it just keeps happening. And in that Chelyabinsk event in 2013, there were so many people who reported the sulfur smell that it was just reported as a fact in science. So it was published in Science, the paper describing this event. It's just stated it's not contested anymore. So yeah, lots of people noticed that smell. And then also when it comes to being too hot to the touch, or hot to the touch, this event happened, which was not expected at all, but this was an impact event. So this is where the object actually hits the ground moving at supersonic speeds, and it forms a crater. And this is the only one that's ever been witnessed in history. It happened in Caracas in Peru in 2007. And the event was reconstructed based on eyewitness accounts plus the physical evidence. It's a beautiful study. And so here we see the bull on the lower right that was knocked over by the shock wave, but it was okay. It was okay. No, it's all right. The gentleman who was on a bicycle whose eardrums were not ruptured by the shock wave, which gives you a sense of like the peak shock pressure at that distance from the impact. And in the house where the shed where there was a window that was shattered by the shock wave and so on. So, but the key point is this, is that this was not supposed to happen. It was not supposed to be the case that an object could make it of this size all the way to the ground at these speeds. And there was an eyewitness who saw that the object who was standing nearby was bright, was incandescent when it hit the ground. So it must have been traveling at least 3 kilometers per second. And that's what the physical evidence showed too. There was shock deformation of the quartz crystals, and that was the smoking gun, as it were, that this was definitely a high velocity impact. So if this can happen, then it suggests that rocks of smaller size traveling at slightly lower speeds, that aren't traveling fast enough to make a crater, but might be traveling fast enough by the time they hit the ground to still be hot to the touch, right? So that's a possibility that I think we have to consider as well. So anyway, this is one of the rare occasions anywhere in the physical sciences where eyewitness testimony has a role, and it had an important role in the case of this event. And I think it's vindicating some of the eyewitness reports from once upon a time. Okay, that's it.